All right, we're going to do another volume of revolution. In a previous video, we did this with the shell method. You can read the directions here, and we got this answer. So there is another method. There's the disk/washer method, and we're going to try that and see and compare the two. So the situation is the same. We're going to take this region, and we're going to revolve it around the y-axis. So, but this time we're going to use the disk method or washer method, and that formula is volume equals, and up here is what we got on the shell method. So the disk method again is pi a to b of big R of x, which is the outer radius, squared, minus little r of x, which is the inner radius, squared, dx. Now, if we're doing this with respect to y, everything becomes y, obviously, and that's probably what's going to happen here. So, first of all, if you're using the disk/washer method, we'll call it washer method because that's more general. This representative rectangle must be drawn perpendicular to the axis of revolution. So this was left over from the shell. I'm going to have to take this rectangle. I'm going to have to rotate it so it looks like this instead. Everything else, though, remains the same. And it's all about measuring. So big R would be the outside radius when you revolve this. So that's going to be this length right here, big R of... Now, this is not R of x, technically. It's R of y. Because when a rectangle is like this, it's going up and down the y-axis. Everything has to be in terms of y. The smaller radius would be formed by this, the bottom, quote unquote, bottom of the rectangle. So all we have to do is measure and we're done. I mean, that's really all this comes down to, is measuring these arrows, but everything's with respect to y. So first thing is, I'm not going to think of this as y equals ln of x anymore. I want it in terms of y. So I'm going to take this y equals ln of x, and I'm going to change it. It was y equals ln of x. I'm going to solve it in terms of y, so I'm going to exponentiate both sides, so you'll have x equals e to the y. So that's what I'm going to refer that. Oops. So it's the same thing, but now it's in terms of y. So now I'm ready to go. Again, all we're doing here is measuring. So let's measure capital R of y first. It's this distance which is x, because it's that's how far you are from x equals 0. So it's x on the x-axis. So, but you can see x here is e. So if you go by the endpoints, this would be e minus 0, or just e. But that's kind of obvious if you look at it. This length here is always e throughout the entire region. So that's pretty simple. R of y is what's changing. So R of y should have a variable, a little r of y, I should say. That will have a variable because it's changing. It's based off this graph. But this distance is still x. So to measure it, you take whatever x is on this end of the arrow point. You're always going right minus left. So this value of x is exactly e to the y, because x is e to the y, and then minus x equals 0. So little r of y is e to the y. So we're basically done all we have to do now is evaluate. So, oh, I forgot my limits. My limits are going from, remember this rectangle is going from um, vertically now. So from here to here. So we're at y equals 0 to this point right here, which is y equals 1. And again, big R of x squared, e squared, minus big R of y squared, minus little r of y squared, which is e to the y squared, or just e to the 2y, dy. And that should calculate the volume, and that should calculate our volume to be this, because if we were right with the shell method, they should match. So here we go. Now, the difference between this and the last problem is this does not require integration by parts. This is an easy integration that you could do before you've learned any of that. So let's do it. The integral of e squared with respect to y. E is a constant, so it's e squared y. Just like if it was 5, it would be 5y. The integral of e to the 2y is 1/2 e to the 2y. You can use u substitution for that, but that's one you can do without u substitution if you just recognize the pattern. And so we're done with the integral. We just have to now plug in our limits. So we're going to start out with 1. So we have e squared times 1 minus 1/2 e squared. That looks nice. Minus, now you plug in 0. The first term is 0. The second term is negative 1/2 e to the first. E to the 0, which is 1. So it's 0 minus 1/2 times 1. I think that should be it. Now I'm going to simplify. How am I going to simplify this one? Well, e squared, 1 e squared minus 1/2 e squared would be 1/2 e squared. Minus negative 1/2 would be plus 1/2. Obviously, you can factor out 1/2, so I have pi over 2. And you're left with e squared plus 1, which is beautiful because when I did this with the shell method, I got hopefully pi over 2 times e squared plus 1. I got pi over 2, or 1/2 pi, perfect, times e squared plus 1. So it's right, unless I made mistakes on both, and this is a big coincidence, but I doubt it. So there you go. Thanks for watching.